After studying this module, you shall be able to transform theoretical activity coefficients into experimentally accessible forms, understand the achievements and limitations of Debye Hückel theory. The first task in the Debye Hückel approach proposed by Peter Debye and Erich Hückel in 1923 is the arbitrary selection of reference or central ion from the assembly of ions in solution. The central ion or the reference ion thus chosen carries a discrete charge of plus ZiE0, while the total charge on the ionic atmosphere or ionic cloud is equivalent to that of the reference ion but has an opposite sign. Due to the attraction between positive and negative ions, there are more ions of opposite sign, and this reduces the effective concentration of ions. Moreover, if the solution is diluted, the separation of ions performs an additional work in order to overcome these inter-ionic interactions, and this represents the deviation from ideal solutions. Therefore, Debye and Hückel derived a mathematical expression to account for the deviation of mean activity coefficients in case of dilute solutions. A true electrolyte completely dissociates into ions when the parent salts are dissolved in water. As a result, the solution generally consists only of solvated ions and solvent molecules. The properties which are dependent on concentration is determined by the interactions between ions. In order to understand these properties, we need to understand about ion-ion interactions in detail. Therefore, to explain ion-ion interactions, we consider an initial state in which ion-ion interactions are absent and a final state in which ion-ion interactions come into play. The initial state is a hypothetical state, as ion-solvent interactions will always be present whenever these ions enter the solvent. Thus, the process of going from an initial state of non-interacting ions to a final state of ion-ion interactions is equivalent to taking an assembly of discharged ions, charging up and setting the electrostatic work equal to the free energy delta G II of ion-ion interactions. This has been shown in figure, which depicts the free energy change delta G II of ion-ion interactions as the electrostatic work of taking an imaginary assembly of discharged ions and charging them up to a solution of charged ions. By definition, this partial molar free energy change is the chemical potential change mu II arising from the interactions of one ionic species with the ionic assembly. Now, we need to calculate the work of charging up the reference ion from zero charge to its final charge ZiE0. Then, the charging work W times the Avogadro's constant Na is equal to the partial molar free energy of ion-ion interactions, that is, the chemical potential of ion-ion interactions. This has been represented in equation 1 as mu II is equal to Na into W. In the previous module, we have learned that the potential psi r at the distance r from the reference is given by the law of superposition of potential. Thus, the potential at a distance r from the central ion, psi r, is the sum of potential due to the central ion and that due to the ionic cloud. That is, we can have this in the form of equations 2 as, therefore, we can write equation 3 as. Now, we shall discuss about the ionic cloud and the chemical potential change arising from ion-ion interactions. the free energy associated with the additional potential arising from the ionic atmosphere is equal to the work required for charging the ions from initial state of 0 to final state of Zi E0, which is obtained by integrating the second term in equation 3 from 0 charge to full charge, that is Zi E0. Thus, we have, applying the limits, we get equation 5 as, substituting equation 5 in equation 1, we get equation 6 as, the relationship between the chemical potential charge mu II arising from ion-ion interactions and the activity coefficient is given by equation 7 as ln gamma I equals to mu II divided by RT. Substituting equation 6 in equation 7, we get equation 8 as, thus the Debye Hückel ionic cloud model for ion-ion interactions has permitted a theoretical calculations of activity coefficients. Now we shall see the transformation of theoretical activity coefficient expressions into testable form. Individual ionic activity coefficients are experimentally inaccessible as it is not possible to have only one kind of ion in a solution. If there are anions, there have to be cations as well, so that the total positive charge is equal to the total negative charge in a solution, which is evidently neutral. Therefore, new terms such as mean ionic activity and mean ionic activity coefficient need to be introduced. Hence, it is necessary to relate the theoretical individual activity coefficient gamma I to the experimentally accessible mean ionic activity coefficient gamma plus minus, so that the Debye Hückel model can be tested. Mathematically, mean ionic activity coefficient is given by equation 9 as, where X is the number of cations with charge Z plus and Y is the number of anions with charge Z minus in the chemical reaction in which AX By dissociates into XA Z positive plus YB Z minus. Gamma plus and gamma minus is the individual activity coefficient of cations and anions respectively. Or we can write equation 10 as, use the Debye Hückel expression equation 8 for gamma plus and gamma minus, we get equations 11 as, substituting equation 11 in equation 10, we get, this is our equation 12. Since the solution as a whole is electrically neutral, so XZ plus must be equal to YZ minus, implies XZ plus plus YZ minus is equals to 0. Therefore, this is our equation 13. Using equation 13 in equation 12, we obtain equation 14 as, we know chi is given by relation 15 as, Ni0 is the total number density of the bulk, that is the number of ions per unit volume. Also, for the electrolyte, we can only measure concentration. Therefore, if Ci0 is the number of moles of ions dissolved per liter of the solution, that is, Ci0 can be said as the number of moles per liter, then Ni0 can be expressed in terms of Ci0 in the form of equation 16 as, where C is the concentration in moles per liter. Therefore, using equation 16 in equation 15, we get equation 17 as, or this can be written in the form of equation 18 as, we have also introduced a quantity which is important in the treatment of ionic solution, that is ionic strength I. It quantifies the charge in an electrolytic solution. Mathematically, it is given by equation 19 as I equals to half summation CiZi square. Equation 18 can be written in terms of ionic strength by using equation 19 in equation 18 as this is our equation 20, or this can be written as chi equals to b under root I. This is our equation 21, where b is equal to, on the basis of the expression 21, equation 14 becomes, this is our equation 22. For a greater compactness, we define a constant A given by, this is our equation 23. Thus, equation 22 can be written in the form of equation 24 as, the negative value for logarithm in equation 24 implies that mean activity coefficient is less than unity. For a univalent electrolyte, that is 1:1 electrolyte, example NaCl, we have Z plus equals to Z minus equals to 1. Thus, I is equals to C. Therefore, log gamma plus minus is equal to minus A under root C. This is our equation 25. Thus, in equation 24 and equation 25, the theoretical mean ionic activity coefficients are in the form directly comparable with experiment. A quantitative comparison of the experimentally observed activity coefficients with those calculated using the Debye Hückel model can be made. Now, we shall see the achievements and limitations of Debye Hückel theory. The approximate theoretical equation derived from Debye Hückel theory, that is equation 24, can be compared with the equation of a straight line, which is y equals to minus mx. Thus, it indicates that the logarithm of the activity coefficient must decrease linearly with square root of the ionic strength. That is, log gamma plus minus is equal to minus a z plus z minus into root I. This is our equation 24. The slope of log gamma plus minus versus root I graph does not depend on the particular electrolyte but only on its valence type. That is, on the charges carried by the ions of the electrolyte, whether it is a univalent electrolyte or a bivalent electrolyte. Moreover, the slope of this graph will give value of A for the solvent. We need to investigate whether at infinite dilution this theory yields the same value of activity coefficient as we would expect from the experiment, that is unity. At infinite dilution, concentration approaches 0 implies I approaches 0. Log gamma plus minus approaching 0 or gamma plus minus approaching 1. This is our equation 25. Thus, Debye Hückel theory proves successful for the infinite dilution case. We should note that the properties of an extremely dilute solution of ions should be the same as those of a solution containing non-electrolyte solutions. If we plot the experimental values of the activity coefficient at extremely low electrolyte concentration with ionic strength, that is, the plot of log gamma plus minus versus root I, it is seen from figure that the plots are linear and they are grouped according to the valence type of the electrolyte. Figure shows the experimental log gamma plus minus versus root I straight line plots for different electrolytes that can be grouped according to valence type. Thus, equation 24 has been found to be valid at limiting low electrolyte concentrations, and it is referred to as the Debye Hückel limiting law. If we examine the experimental plot of log gamma plus minus versus root I curve, at high concentrations the Debye Hückel limiting law fluctuates. The plot of log gamma plus minus versus root I is no longer a straight line but a curve as shown in figure. Moreover, the curves do not only depend on the valence type 1:1 or 2:2 but also on the particular electrolyte. It can be seen that at very low concentrations the Debye Hückel law is the law for the tangent to the log gamma plus minus versus root I curve. Thus, the model needs to be improved at higher concentrations because the value of mean activity coefficient even exceeds unity in some cases. Figure shows the experimental log gamma plus minus versus root I curve is a straight line only at extremely low concentrations. Now we shall summarize what we have learnt in the module. Debye Hückel theory permits theoretical calculation of activity coefficients, that is, theoretically derived mean activity coefficients can be related experimentally as where A is equal to and B is equal to. It is also known as the Debye Hückel limiting law. Debye Hückel theory is valid only in the limit of low concentrations. The theory falters at high concentrations.